Today I will be doing another Faraday's problem, and the problem is as follows. A thin copper wire with radius r is placed in a spatially uniform magnetic field given by B is equal to negative x times 10 sine 0.5 t Tesla. If the radius r is increasing at a rate of 50 centimeters per second, starting from r is equal to 0 at t is equal to 0, what is the direction and magnitude of the induced current on the ring when the radius r is at 1 meter? Define the direction clearly on a sketch. The resistivity of the wire is 0.2 ohms per centimeter. So, just like any Faraday's problem, let's just start off by finding the flux, which is just B dot A. So, plugging in our B, we simply get negative 10 times sine 0.5 t times the area. And the area, since it's a circle, is simply pi r squared. So now that we have our flux, we can also find our EMF, which is simply just going to be negative dV over dt. Plugging in our flux, we get negative d over dt times negative 10 sine 0.5 t times pi r squared. So taking out our constants just to make our life easier, we can take out negative 10 and pi. And in this case, since r is changing, we can't take that out. So it will look something like, since it's also negative, so it will become positive. So taking out the 10 and pi, we'll get 10 pi d over dt times sine 0.5 t times r squared. Again, I simply just took out the 10 and pi, made it positive because we have two negative signs. And we cannot take out r because r is changing with respect to time. So simply we just use product rule, and we will simply get 10 pi times, taking the derivative of the r squared first, I'm just going to do it this way, you will get 2r, and because of chain rule, when you take a derivative of r, which will simply just be dr dt times sine 0.5 t plus taking the derivative of the sine 0.5 t, you will get 0.5 times cosine 0.5 t. So just writing that down, we get cosine 0.5 t, and then because of chain rule, it will be multiplied by 0.5, and we'll leave r squared alone. And this will be our VEMF. So now we can also find our induced current, which is simply VEMF divided by R. And I'm going to just plug in what we had before for VEMF, which is simply what we just solved for. We will just get 10 pi times 2 times r dr over dt times sine 0.5 t plus cos 0.5 t times 0.5 over r squared divided by the total resistance. And in this case, what is our resistance? Well, since resistivity is given, we simply just need the length of the circle. In this case, it will just be 2 pi r. So 0.2, which is the resistivity, times 2 pi r, or the circumference of the circle, or the thin copper wire. And this will give us the length. So now that we have our equation for our I induced, let's just plug in the radius and time. Since we are interested at when the ring is at 1 meter, or the radius is at 1 meter. But the question is, when does this ring even reach 1 meter? So, just doing some simple math, we know that it's growing at a rate of 50 centimeters per second. And this is simply just going to be 0.5 meters per second. So time would then just be, if we're interested at 1 meter, divide this by 0.5 meters per second, and we'll just be left with 2 seconds. And then we also know that the rate of change with respect to time is 50 centimeters per second. So we can also put that into our formula up here. Again, we know that dr over dt, or the rate of change for the radius, is 0.5 meters per second. And this is our time. So, plugging these into our I induced formula, we will get 10 pi times 2 times the radius, which is just simply going to be 1, times the rate of dr dt, which is 0.5, sine of 0.5 times 2, plus cosine of 0.5 times 2 times 0.5 times the radius, which is simply going to be 1 squared. Again, the radius is 1 because we are interested at finding the induced current when the radius r is at 1. And this is the radius. And all of this will be divided by 0.2 times 2 pi times 1. So, just to simplify this even further, we will get 10 pi times 2 times 0.5 sine of 1 plus 0.5 cos of 1 divided by 0.2 times 2 pi. And plugging in sine 1 and cosine 1 into your calculator will give you these values. You know cosine of 1 is equal to 0.54 rads, and sine of 1 is equal to 0.84 radians. So we will get 10 pi times 1 times 0.84 plus 0.5 times cos 1, which is 0.54. All of that divided by 0.2 times 2 pi. Then issue this 10 pi divided by 0.2 times 2 pi will give us 25 times whatever is inside, which is 0.84 plus 0.27. And this is an I induced. And you will get a value of 27.75, which is equal to an I induced. This is also equal to about 27.8 amps. So we still need to find the direction of this induced current. So in this case, we have two contributions. Our first contribution is that the radius r is increasing at a rate of 50 centimeters per second. So first is increasing radius. And then the second is the B field, which is also changing, which is negative x hat times 10 sine 0.5 t. So I'm just going to draw the diagram so I can use my right hand rule. Z, Y, this is our circle. Then all that means is our x is going to come out of the paper, x, y, and z. X is coming out. So, just by inspection, or whatever you want to call it, increasing radius will just mean that more flux will be introduced. So that means that, according to Lenz's law, our induced current will go the opposite direction of the B field, and we know that the B field is going into the paper. So all that means is increasing radius will result in an induced current that's going counterclockwise. Then we should also realize that sine is an increasing function, which will mean that we will also have more flux. So the induced current will also go counterclockwise. So in this example, we get something that's pretty nice to work with. Both of them will be counterclockwise, so that we know that the induced current will simply just be counterclockwise, going this direction. And then again, we know that our induced current is simply equal to 27.8 amps. So again, you can use inspection if you would like and realize that increasing radius results in more flux, which means that induced V will be coming out, which will result in a counterclockwise induced current. And the same methodology can be applied to the B field, because sine means that's increasing initially, which will also result in an induced current that's going counterclockwise.